So, in this tutorial video, we will uh, means talk about this finite morphism. First, recall the definition of finite morphism. Recall, let x, y be pre-varieties and f be a morphism between these two pre-varieties, a morphism of pre-varieties. Then f is called finite if for all uh, affine open V inside Y f inverse V, this is affine open in X and the morphism from f inverse V to V, this is finite. Meaning that is this O of f inverse V, this is finitely generated OV module. Okay. So, this was the definition of a finite morphism between two pre-varieties. Now, we want to prove a proposition. Suppose x and y be two pre-varieties and f from x to y be a morphism of pre-varieties and suppose y has a affine open cover Vi, this is a affine open cover. Now, y has a affine open cover such that this f inverse Vi is affine for each I and this morphism from f inverse Vi to Vi, this is finite. So, this proposition states that for finite morphism we do not need to check for every affine open subset of Y, but if we have a affine covering of Y such that this property satisfies, means this f inverse Vi is affine and f inverse Vi to Vi the morphism that is finite, then it will be a finite morphism. So, we do not need to check for every affine open subset of Y, we can means check for affine covering of Y. So, that is what this proposition says. So, in algebraic geometry means we will see this similar kind of results in many places. So, the idea of the proof is more or less same for all these results. So, let me first means outline the means what is the idea to prove such results. Okay, proof. So, here we have to show that for any affine open means we have a affine open covering such that this property satisfies, such that this f inverse Vi is affine and f inverse Vi to Vi this is finite. So, for now we have to show for any affine open subset of Y, say V, this as a property holds. So, suppose let this V be a affine open subset of Y. Now, we denote this ring of regular functions of Vi by say Ai, ring of regular functions of F inverse Vi by Bi, ring of regular functions of V by A, and ring of regular functions of F inverse V by B. Now, because these VIs are affine open, so these are this AI and BI, and also AI, BI as well as A. These are all finitely generated integral domains over this algebraically closed field K. Okay. So, now what we have to show? We have to show that for showing that F inverse V is affine, we have to show B is sub finitely generated integral domains over K. That we have to show, and we have to show that B is finitely generated A module. Okay, these two things we have to show. Now, for that, okay, also we have that all these BIs is a finitely generated AI module. So, we have this. Okay. Now, we know that say this DG means where G is a non-zero regular function on Vi, they form a basis, means DG means where this G doesn't vanish. So, this collection form a basis for Vi, and this DG they are affine. DG is affine, means this is isomorphic to some affine variety. So, yes, with this ring of regular functions, this is isomorphic to AI, okay. So, we denoted this thing as means sorry, O of Vi as AI, right. So, this will be localization at G. So, we know this. Now, we have this map, this O of Vi to O of F inverse Vi. This is F, say this map. Now, this is our AI, this is our Bi. This is say at Vi. Oops. say this is Fi. Now here G goes to G composition F. Now we know that Bi is a finitely generated A module, right? AI module. Bi is a finitely generated AI module. So this will be true that Bi localization at this G composition F, this is a finitely generated AI localization at G, this module, because this G goes to G composition F. This is the image. G composition F is the image under this uh, ring algebra homomorphism, K algebra homomorphism. So also we have this F inverse dg. This is nothing but d of G composition F. So this implies that so there exists an affine open covering of V say Wj, such that this F inverse Wj, this is affine, and F inverse Wj to Wj, this map is finite. So we reduce to the case when we can reduce to the case when Y is affine, we can say like that. So now we denote this O of Wj to be Cj, say, and O of F inverse Wj be say Dj. They are also finitely generated integral domains over K, and also Dj is finitely generated Cj module for all j. So we have this. Let H be a regular function on V such that this d of H, this is inside Wj, this is inside V. Okay. Now we have this map, this OV to OWJ, we have this map. Under this map, say H goes to H bar. Okay. Now exercise, I will not prove this exercise. This regular functions on d of H, this is actually this is isomorphic to AH, we know. Now we have to show that this is isomorphic to Cj localization at H bar. So this thing we need to you have to check, you have to prove this. Now if we assume this result, this fact, so there exists finitely many Why I am writing finitely many, I am not going to explain, just think about it. There exists finitely many dh where h is a regular function in V which covers uh, uh, which cover V are affine, which covered V are affine uh, which covered V and uh, this F inverse dh to dh d of h, this is finite, this is finite uh, and this is affine, this is affine and this is affine. So we have means there exists finitely many such dh. Okay. Now one can also again show means see that this the regular function on f inverse of d of h, this is isomorphic to dj localization at h bar composition f. So we can show that means it is easy to see. So it means that there exist some say alpha 1 up to alpha r, they are inside A, where A is nothing but this O of V, such that uh, this V is union of this D of alpha I, where I runs from 1 to R, and yes, and F inverse D of alpha I, this is isomorphic to this is isomorphic sorry, this not this is isomorphic to here to D of alpha I, this is finite. So we have this. Okay. Now from here we have to show that means that V F inverse V, that is affine, and this F inverse V to V, that is finite. Okay. Now B is a finitely generated integral domain over K. So you have to do a little work, means little algebra you have to do. Then we can show that V is a finitely generated integral domain over K. And now for the now hint for this part 2, means we have to show that F inverse V to V, this is a finite map, or in other means in other language this O of F inverse V, this is integral over sorry, this is a finitely generated O of V module. So that we have to show. Now we reduce we reduce to a purely algebraic problem. Uh, Means where this alpha 1 to alpha r, this is inside A, such that because this d of alpha I is the covers this V, so it says that this elements generates the whole A, and because this we have this A to B, we have this map where alpha I say goes to alpha I bar, then this alpha I bar, this is finitely generated. B localization at alpha I bar is finitely generated. A localization at alpha I bar, alpha I module. So we have this. Now we have to show that B is finitely generated A module, and this is easy. You have to consider the generators of this B of alpha I bars as alpha I alpha means A localization at alpha I, this as the this module. Then consider for if all alpha i's, means consider those generators, and you have to do means observe something to find the generators of B as a means finitely generated A module. Okay, so this is easy, means this is again an exercise. Now if we complete this, then we are done.